Welcome to Excel 2013 Statistical Analysis video number 22. And if you want to download this workbook and follow along, click on the link below the video. Oh, this video, we get to talk about one of the more amazing statistics, Z, or Z-score. It'll tell us the number of standard deviations away from x bar or mean of particular x's. Now, why is this so powerful? Well, let's just start off with an example. Here's you. You got 83 on your calculus test. And your brother comes home and goes, ha, I got 86. Well, immediately you say, yes, but did you do above average or below average? That's where Z comes in. So we know the mean was 76 for your test, and you got 83. Well, just visually, we can see, hey, you're above average. Oh, look at this. The mean was 91. Your brother got 86. So visually, we could see that's below the mean. Now, we want an actual measure that tells us exactly for any data set the relative position of a particular x compared to the mean in any data set. So what calculation is that? It's the Z. So let's go ahead and equals open parentheses. You take the particular x and subtract the mean, close parenthesis. Now, before I complete this calculation, I'm going to enter this, Control Enter. And what is that? That's the deviation. You're exactly 7 points above the mean. F2, we always want to divide it by the standard deviation so we get number of standard deviations above or below the mean. Well, let's come down and do the same calculation for your brother. Equals open parentheses, particular x minus a bigger mean. That means when we enter this, the deviation, of course, is negative, minus 5 points below the mean. But we want it in units of standard deviation. So F2 divided by the standard deviation for this data set. Boom, minus 1.25 standard deviations below the mean. Because we've converted the deviation to units of standard deviation, we can now directly compare two different data sets. You're 1 standard deviation above the mean. Your brother's minus 1.25 deviations below the mean. Now, this is also called the standardized value because now we have a standardized value that we can compare. Hey, guess what? Standardize, that means there's a built-in function called standardize. It will calculate Z-score or number of standard deviation. Now, there's our particular x, comma, there's our particular mean, and comma, there's our standard deviation. Boom, Control Enter. It'll give us exactly the same thing. 1 standard deviation above the mean. It's a relative location of a particular x in a data set as compared to the mean in units of standard deviation. That means we have a standardized value that we can use to compare with other particular x's in other data sets. We could do standardized down here. X, comma, mean, comma, standard deviation, Control Enter, minus 1.25 standard deviations below the mean, relative location of a particular x in a data set as compared to the mean in units of standard deviation. So what is Z? Number of standard deviations. Now, I kind of like to do the calculation this way because it emphasized deviation divided by standard deviation. You could do it whichever way you want. Now here, check out, there's Joe. Joe's score on the calculus test equals open parentheses his particular score minus the mean. Now this one we can visually see without even calculating. The deviation, 0. He got exactly equal to the mean. F2, hey, and when we divide this by the standard deviation for the calculus test, we still get 0. A Z of 0 means you are exactly on the mean. Now, we definitely want a measure that will allow us to compare particular x's in units of standard deviation across different data sets. So that's our measure, the z-score. Now let's scroll down here because visually it helps us to understand what the z-score means. Here's all the calculus scores from the data set. There's the mean. Standard deviation of 7 with an x bar of 76. You're right here, 83. Exactly 7 points above the mean. Divided by the standard deviation of 7, that's 1 standard deviation. So visually, you can see, yeah, you're above the mean. Hey, what about here? This is your brother's history test. X bar is 91, standard deviation of 4. Looks like you're 5 points below. So you're definitely below the mean. But in terms of standard deviations, you're minus 1.25 standard deviations, or 1.25 standard deviations below the mean. So Z, incredibly useful. We'll use it throughout the class. When you're listening to people talk out there in the media, in articles you're reading, you'll hear people talk about number of standard deviations. Whenever they're talking like that, they're talking z-score. Now let's go over to our next sheet, Z2. Now sometimes you're given the whole data set with all the particular x values instead of just a single x value. So here we can easily calculate z. We've already calculated x bar of 60, sample standard deviation of 13. Let's go ahead and calculate z for every single one of these values. Open parentheses, particular value, minus, and we'll get our x bar, F4 to lock that all the way down, close parentheses, and divide it by sample standard deviation, F4. Control Enter. Double click and send it down. There's all the particular z values. So right here, this person got 39. They're minus 1.62 standard deviations below the mean. Hey, let's go over to our next Z3 sheet. Hey, look at this. Here we got human heights here. The average height in inches was 71 inches with a standard deviation of 4 inches. All the particular x's, we want to see number of standard deviations away from the mean each particular x's. So we equal open parentheses particular x minus our x bar, and I'm going to F4 close parentheses, and we're going to divide it by the standard deviation. F4 to lock that. Control Enter.
0.50.
Double click and send it down. You know, I didn't check that last one. I'm going to go down to one of these and F2 key to check to see, did we get relative cell reference? Yes, we did. Did we lock and lock? Yes, we did. Each one of these, oh, look, this person, 61 inches, minus 2.5 standard deviations below the mean. Oh, look at this person, exactly right on the mean. Now, z-scores are incredibly helpful in all sorts of ways. We want to go over and we're going to talk about the Chebshev rule, and then we're going to talk about the empirical rule. Both of these rules are going to help us make statements about data sets using the z-value. So let's go over to Chebshev. Now here's the notes that are over on the note sheet, of course. Chebshev's theorem allows us to make statements about the proportion of data values that must be within a specific number of standard deviations of the mean. For example, we want to be able to make a statement like, hey, 75% of the students must have a test score between 34 and 86. Here's our formula. But the real power right here of this theorem is it applies to any data set regardless of the shape of the distribution. The empirical rule we'll see in just a second is only for a specific type of distribution. But this rule will work for any distribution. Now, here's our formula, 1 minus 1 divided by z squared, where z is number of standard deviations away from the mean. And z has to be bigger than 1. That says that up here. Now, our test average was 60 with a standard deviation of 13. Now, before we calculate values, let's just use this to calculate the proportion of values that must lie, for our first example, within plus or minus 2 standard deviations. We're just calculating the proportion, and then we'll figure out the two ends which will represent plus or minus 2 standard deviations. So the proportion equals 1 minus 1 divided by RZ, plus or minus 2 standard deviations. We just need to put it in as a positive, caret 2. Now, this formula right here will work perfect the way it is, because guess what? Order of operations, exponents get calculated first. Oh, and then the division will happen. Oh, and then the subtraction. So we can simply Control Enter. At least 75% of the data values must be within plus or minus 2 standard deviations. And this can be any z greater than 1. I could put a 3 in here. At least 88.9% of the data values must be within plus or minus 3 standard deviations of the mean. Hey, 1.6. Control Enter. Oh, whoops. Guess what? We're being tricked by number formatting. And I can see up in the formula bar it says 1.6. I'm going to increase the decimals. But now I'm going to keep this 2. So 75% plus or minus 2 standard deviations. Now let's figure out the low and high. The low is 2 standard deviations below, and the high is 2 standard deviations above. Below and above what? Equals, it's the mean. So we take the mean, 60 points. The low, we're going to subtract 2 standard deviations, that's the number 2, times the actual standard deviation. That means 26, that's 2 times 13, subtracted from 60, Control Enter, we get 34. So that'll be the low end of this percentage statement. For the high, we're going to take our 60, that's our average, and add how many standard deviations? 2 times the actual amount of the standard deviation, 13. Control Enter. So at least we can refine our statement now. At least 75% of the data values must be within 34 and 86 points. Now let's try it for 3 standard deviations. Equals 1 minus 1 divided by our 3 standard deviations, caret 2. Control Enter. Awesome. Now we have 88.9%. Now we can calculate our low and high. Equals, hey, we got our 60. That's the mean. Subtract 3 standard deviations times the amount of standard deviation. Enter. So 21 will be our low end. Equals 60 plus 3 standard deviations. So 3 times 13. And boom, we have our high. So at least 88.9% of the data values must be within the low of 21 points and the high of 99. Now let's look at one last example for Chebshev's theorem. Hey, percent given 1.8 standard deviations equals 1 minus 1 divided by number of standard deviations, caret 2. So boom, there's our statement. According to Chebshev's theorem, at least 16 or about 69% of any data set will be within plus or minus 1.8 standard deviations of the mean. Now, in all of these situations, we actually calculated the percentages. But because people often talk in terms of 1 or 2 or 3 or 4 standard deviations, usually for this rule and for our empirical rule, there'll be standard statements that people are aware of or have memorized. So for this particular rule, Chebshev's rule, within plus or minus 2 standard deviations, at least 75%. For plus or minus 3 standard deviations, at least 89. Plus or minus 4 standard deviation, at least 94%. Now, one thing about this rule is we're given the formula to calculate the percentage. We're now going to go look at the empirical rule, and we'll see that we're not going to be given the formula. We won't get that till Chapter 6, but we will see this kind of statement. So let's go over to empirical rule. Now, the empirical rule, guess what? It has to do with bell-shaped distributions. Now, we looked at our human height example, and that's a type of data that does tend to follow a bell-shaped distributions. Other distributions that oftentimes follow this bell distribution, things like prices or some manufacturing situations like filling bags of lettuce or boxes of cereal. Now, here's the rule. approximately 68% of the data values will be within plus or minus 1 standard deviation, 95% within 2 standard deviations, and almost all of them, or 99%, will be within 3 standard deviations. Now check this rule out. This is much more wide in its interval. Let's just go check out 2 standard deviation. Here it's almost 95%. Let's go back to Chebshev's. 2 standard deviations is just 75%. Well, the reason that we would use this rule with a much smaller percentage for a given interval of standard deviations is because we don't know anything about the shape of the distribution. So when we go over to the empirical rule, the reason we're allowed to make a larger percentage statement about a given number of standard deviations is because it's bell-shaped. The innate shape of a bell shape, or normal distribution, or Gaussian, or symmetrical distribution, it means that there's more values in the middle, many more values. But as we go up or below the mean, it tails off fewer and fewer values in either direction. So because most of them are in the middle, we get to make a much larger percentage calculation. Now we will actually learn exactly how to calculate 68, 95, and 99 in Chapter 6 when we learn all about the normal distribution. But here in this chapter, because we're talking about number of standard deviations, which is z, we're going to talk about the empirical rule, 68 plus or minus 1 standard deviation, 95 plus or minus 2 standard deviation, and almost all are 99 plus or minus 3 standard deviations. Now, once you look at lots of past data, like for human height or manufacturing or prices, and you see through your histograms or dot plots or whatever you're looking that the distribution tends to be bell-shaped or symmetrical, then we can use a curve like this. And again, we'll calculate this exact curve in Chapter 6. But here, let's check it out. We're talking about z's, right? Right in the middle. There's our height. Average height, 71 inches, 0z. Between plus or minus 1 and minus 1 standard deviation, we got a 67 and 75%. So what does that mean? Oh, I've color-coded this and have this legend up here. All the area, including way out in the upper tail or way down in the lower tail, all the area is 100%. All possibilities. Actually, from the mean all the way down is 50%, and from the mean all the way up is 50%. But between these plus or minus 1 standard deviation, that's 68%. Between plus or minus 2 standard deviation, all that area that we'll calculate in Chapter 6, that's 95% representing plus or minus 2 standard deviations. And look at there's that plus or minus 3 standard deviations, almost all. Barely, you can barely see it right from there all the way over to here. That's why sometimes you hear people calling outliers plus or minus 3 standard deviation. It's just so improbable that you would get a value out here. Although it is possible, there is a very remote possibility that those values can occur. Now let's go see how this rule plays out in this chapter. Because remember, we're just trying to get a handle on z's, 1z, 2z, 3z, number of standard deviation. So here's our rule. We're not going to calculate percentages, but we can definitely calculate the lower and upper numbers. Given, for our first example, 68% of the values, we're going to start off, hey, 71 inches minus 1 standard deviation times the amount of the standard deviation. So the lower height for our 68% rule, 67 inches. The upper, hey, we're still taking our mean plus 1 standard deviation times the amount of the standard deviation. So about 68% of the heights will be between 67 and 75 inches. Down here for 2 standard deviations, hey, we're still taking the mean. It's the lower end, so subtracting 2 times that 4 inches, which is our standard deviation. So there's for 95%, the low end is 63 inches. So the upper equals, hey, we still got to take that 71 inches and add to it 2 times the amount of the standard deviation, 4 inches. So about 95% of the heights will be between 63 and 79. Now, why is this so important? Because these will give us ranges of reasonable values. You know, if we go out and take a sample and get a mean or an x-bar and an average between these two values, you know, that seems like that sample really represents the population pretty fairly. Same with this one, 95%. We still have a 5% risk that we might be making an error because we're not including everything here. If we really want to be sure, then we would do 3 standard deviation. Hey, I'm still taking the 71 inches minus 3 standard deviations times the 4 inches. So 59 inches is the lower. The upper 71 plus 3 times 4 inches. Control Enter. So about 99%, or basically all the values we would expect to find between 59 inches and 307. I calculated that wrong. Here, I'm going to edit this. I'm going to point there. I meant to get 3 standard deviations times our 4 inches. Wow, it'd be amazing to find a 307-inch person, right? So most of the time, almost all the time, we're going to meet people that fall into this range. But of course, we know that it is possible to be outside this range. Now, that's human height. That's a distribution that tends to be bell-shaped. Let's look at another example. Hey, we're going to talk about gas prices. So the average price is 2.31 with a standard deviation of 0.12. We're assuming that the population is bell-shaped to use this rule. The lower, oh yeah, OK. So for 68%, I'm going to say, hey, the average and subtract 1 standard deviation times 12 cents. So the lower would be $2.19 for a gallon of gas. The upper, we're going to take our mean, $2.31, and add to it 1 standard deviation times the 12 cents. So about 68% of the prices will be between $2.19 and $2.34. Now I'm actually going to come up here and see that mean. I'm going to hit, my cursor's touching the cell reference, F4. Standard deviation, F4. Enter. F2 to put it in edit mode. I'm going to F4 that $2.31 and F4 the 12 cents. Control Enter. Because I have the plus and the minus and their relative references looking at that 1 standard deviation, I'm going to copy this. And I'm going to paste it down here, Control V. If you put it in edit mode, F2, you can see that works perfect in terms of cell references. So at 2 standard deviations, given our average of $2.31 with a standard deviation of 12 cents, about 95% of the prices should be between $2.07 and $2.55. Copy. Control V. So down here for 3 standard deviations, given our gas data up here, we would expect all of the values we encountered would be between $1.95 and $2.67. So gas prices. Let's look at another example, and we'll delve into manufacturing examples in Chapter 6, where we actually go out, we'll take a sample of a machine that's running, we'll compare it to the population expectations, and if we get a sample that falls in between one of these ranges, we'll assume the machine is filling correctly. So here, right on the box, it says 32 ounces. We know the standard deviation is 0.35 ounces. I'm actually going to put OZ here. These are not exactly meaningful without the units, so those are ounces. So within 1 standard deviation, hey, I'm going to say give me the 32 ounces, F4, minus 1 standard deviation relative cell reference times our standard deviation F4. All right, so when I hit Enter, that gives me the lower amount equals the mean 32 ounces, F4 plus 1 standard deviation relative cell reference times the 0.35 ounces. That's the standard deviation, F4. Control Enter. So about 68% of the weights will be between 31.65 ounces and 32.35 ounces. I'm going to copy this and paste it down here. So For our 2 standard deviations, our empirical rule says 95% of the weights will be between these upper and lower weights. Now, for this particular example, if we went out and got a sample mean and it was below 31.30, so we actually got a 31-ounce sample off of a machine, it becomes likely then that the machine is not filling correctly. So really, with this empirical rule and the low and upper end, it gives us a range because samples don't exactly match the population. But at least it gives us a range of values that seem reasonable. If our x bar, our sample mean, falls between these two values, we assume the machine is filling correctly. If it's outside, then we shut it down and check it out. Now I'm going to Control V down here. 99%. If we got a value below 30.95 or above this, we're 99% sure that that machine is not filling correctly. Now let's look at another example. In all these examples, we calculated the lower and the upper. And we're kind of going to do things a little bit backwards in this chapter, because later we'll see how to calculate it using the norm, dist functions. But here we want to try and apply our rule. Now, here's a little chart I made. 68% of the values would lie between -1z and +z, 95% between 2z and -2z, and of course 99% between plus or minus 3z's. But also, check this out. If right down the middle, that's a symmetrical curve, and everything on the upper end is 50, everything on the lower end is 50. So we can make statements like, if we know the gas average is $2.31 right there, we could say something like, what's the probability of getting a value from our sample that's $2.31 or higher? There would be a 50% chance that that would occur. All right, so let's go over here and look at some examples. Now, actually, what I've done, and I didn't mean to do this, is here's our, in this chapter, we're given 68, 95, and 99. I'm just going to divide each one of these in two, because then if we get a question that involves just half of it to some 2z or 1z, then we can immediately look at our little chart here. So equals 0.68 divided by 2. Oh, 34. That's how I figured that this is approximately 34. 68 divided by 2. So we can simply copy that formula down, and in each case it will give us exactly half. So here's our first question. This is our gas example, $2.31 with a standard deviation of 12 cents. What is the probability of getting a price between $2.31 and $2.51? Well, in this chapter, they're just going to give us even standard deviations. Later, they won't. But let's go ahead and calculate the lower z, which is number of standard deviations. Particular x. Subtract our mean F4, close parentheses, divided by our standard deviation F4. Control Enter. Well, that one we can I. That one is definitely $2.31. Control C and Control V. Notice that was a relative cell reference, but these ones were locked. OK, so we need to calculate the probability between 0z and 2z. So now we're looking over here. There's a 0z all the way up to 2z. Well, I know that's 0.95. So when I divide it in 2, I get 0.475, or 47.5%. So I'm simply going to say equals this. Again, we're just trying to get our hands around this concept. In this chapter, later we'll figure out exactly how to calculate that without using something like this, because we're limited to these integer values of standard deviation. All right, so now the question is, what is the probability of getting a price between $2.07 and $2.43. Hey, I'm going to click down here, but I'm going to come up here because I already created the smart formulas with relative and absolute. Control C and Control V. So here I can see there's a particular value. Subtract the mean, divide by the standard deviation. And same here. Boom, $2.43. Subtract that $2.31, divide by the 12, and it gives me a plus. So now I need to calculate the area, or the probability, between -2 and 1. Oh, there's -2 and 1. Well, I know that from the midpoint to -2 is 0.475. I also know from the 0 up to the z, that's 0.34. So if I come over here, equals boop, plus boop. So the probability of getting a price between 207 and 243 is approximately 81.5%. Our last example, what's the probability of getting a gas price above $2.19? Well, we better calculate our lower z, and then it's everything above it. Equals, open parentheses, our particular z minus the mean, close parentheses, divided by our 12-cent standard deviation. Oh, it's -1. Well, the -1 is right here, and we're trying to figure out everything from there above. Well, I know everything from the 0z up is 50%. And everything from the 0z to minus z is 0.34. So down here, I'm simply going to say equals 0.5 plus 0.34. I know this is kind of clunky in this chapter to do it this way, and I promise later we'll get a better way to do that. But there it is. We still can do it. We can still calculate this even though it's a little bit clunky. The probability of getting a price above $2.19 is approximately 84%. All right, so the purpose of this is for us to get used to these standard 1 standard deviation, 2 and 3 standard deviation probabilities or proportions when we have a bell-shaped distribution. All right, so we talked about empirical rule for bell-shaped distributions. Remember, it's all about number of standard deviations in z. We talked about Chebshev's rule. Here we could calculate the percentage, and we had our 2, 3, and 4 standard deviation percentages, all about z's, number of standard deviations. And then we talked about z on a data set, z on another data set, and even our initial calculation where we compared you and your brother using z-score. All right, next video, we're going to talk about 5 number summary and box plots. We'll see you next video.